Opportunity to share this webinar today. Really pleased to be invited. This was a project that took place several years ago, but as more time goes on, I feel like we have a better and better understanding of what took place. I was really fortunate to be involved in this large-scale test program on seismic isolation. It was really anticipated to be a run-of-the-mill proof of seismic resiliency, but instead ended up unearthing some really interesting issues that hadn't been observed before. So as an academic, I had a lot of fun exploring these issues. Over the years, I think the message has evolved a little bit and the takeaways have evolved. And I try to focus on what really matters in terms of providing resiliency through seismic isolation, where we're at now, and what issues still need to be overcome. So a little bit about the introduction to the test program. This was a collaboration of two NEES projects and the NIED agency in Japan. NEES was the Network for Earthquake Engineering Simulation, the predecessor to NERI. This testing took place at Japan's e-defense facility in August 2011. A couple years later, we had a wrap-up workshop with 30 practitioners, and several dissertations and theses have resulted from this project. It certainly takes a lot of people participating and helping to pull off a large project like this. And while I can't read every name, I'd like to acknowledge all the investigators, academic collaborators, and industry collaborators and sponsors that contributed to the project. So with a national audience like this, it's hard to know exactly where to pitch the presentation. To allow myself enough time to talk about the good stuff, I'm going to presume some basic background knowledge on seismic isolation. I presume that most people know that the code performance objective is life safety for design level earthquake, which is achieved by designing for controlled damage. And that means if we look at elastic design spectrum, for a given earthquake, we don't actually design for that, but instead take a force reduction factor, which is on the order of 4 to 8 for typical buildings, and we design for those reduced set of forces. I presume that everyone knows a little bit about seismic isolation, the concept to place a flexible layer beneath the building when the application is for buildings. Causes the superstructure above to remain essentially rigid. The flexibility or the natural period of the system is determined by the flexibility of the isolators, and we can control that and as a result push the natural period way out into this lower force region of the spectrum. So the lengthened period leads to reduced force demands, and so much so that it's considered economical to design for the elastic forces. I presume that the audience knows a little bit about the different types of seismic isolation devices that are used, elastomeric or lead rubber bearings being one main class, and sliding bearings, mainly friction pendulum bearings, being the second class. In both cases, the general force displacement relationship of the isolators can be represented by a bilinear curve. The post-yield stiffness determining the natural period, and then the area of the hysteresis loop determining the energy dissipation and effective damping. An elastomeric bearing consists of layers of rubber and alternating with steel shims. The flexibility of the rubber determines the post-yield stiffness. If it's a lead rubber bearing, a lead core will be press fit into the center, and that determines the energy dissipation. The other major class of sliding or friction pendulum bearings consists of an articulated slider, slides around in a curved dish. The curvature provides the restoring force and determines the post-yield stiffness, whereas the friction coefficient determines the area of the hysteresis loop. And then the trend in recent years has been to move from single pendulum to double and triple pendulum bearings with multiple sliding surfaces and that can be optimized for different intensity earthquakes. And here's a picture of the triple pendulum. So before we start talking about this test, let's say that when we began to plan our test program, we were aware that there was a large history of shake table testing on isolated buildings. Here's a sample of the different tests and the main objectives they focused on. But, you know, throughout history, the trend has been the same, and pretty much all tests come up with the same conclusion: no damage to the structure, even in large motions. So you might ask, well, why do we need to do another test? I show some of the different specimens that were considered in these tests, and as you look at them, you might be struck that they all sort of share some characteristics in common. The vast majority are reduced scale structures. Because of the reduced scale, they tend to be bare frame, lacking realistic floor systems, and instead use added mass to achieve the desired inertial properties, but don't behave the same way as a realistic floor system. Also, we always said that the building protected non-structural components, but none of these tests really had non-structural components in them to prove that. And the table shaking was generally 1D or 2D bidirectional horizontal with no vertical input. So with this test program, we were able to sort of take the test to the next level in terms of the reality of the specimen that we were looking at. The scope of the test program, we actually tested this building. It's a steel moment frame building in 3 different configurations: isolated with triple friction pendulum bearings, isolated with a hybrid configuration of lead rubber and cross-linear bearings, and I'll explain about the cross-linear bearings in a minute, and then fixed at the base. The specimen itself was not designed specifically for this project, but was designed for a previous project. It had been tested 2 years prior, and it was sitting out in the fab yard, basically undamaged. It was a very suitable specimen for this planned test: 2-bay by 2-bay steel moment resisting frame, but designed by Japanese standards and in particular for value added building. Therefore, it was very stiff, a period of 0.7 seconds, and very strong, with a first plastic hinging mechanism of about 0.7 times the weight. So very suitable for this program. We had some specific, since we had 2 different isolation systems, we had specific objectives for each. The program was really designed around the triple pendulum system, and the overall concept was a system level demonstration of the seismic resiliency to a very large event. We wanted to show proof of concept that the isolation really can provide continued functionality and minimal disturbance to contents. Along those lines, we also were aware of the trend, at least in the US, to move to very long period isolation systems, like 4 to 5 seconds, very large displacement demands, and we wanted to show that this design concept was effective, the bearing and the overall performance would do well even under very large near fault motions. The second system with lead rubber bearings came about a little bit later in the overall concept. This was sponsored by the Nuclear Regulatory Commission, which is actively evaluating, and I believe still is, evaluating lead rubber bearings for use in base isolated nuclear power plants. And so they wanted to look specifically at the performance evaluation of the bearings, full scale bearings subjected to large displacement demands and potential stability concerns. How would they perform? With regard to that main resiliency objective, we needed non-structural components. This is where the second NEES non-structural project got involved. They designed an integrated system of ceilings, partition walls, and piping, which were installed on the 4th and the 5th floor of the building. Nearly identical configuration over the 2 floors, placed high. Because of this project, we added the fixed base configuration to show comparison. We knew the acceleration demands would be highest on the upper 2 floors. Here's some pictures of the nearly completed non-structural components. You can see a suspended ceiling system. You can see partition walls in the distance and all around the outside of the building. This is a view above the ceiling plenum showing the fire sprinkler piping system. And then the bottom 2 pictures show we were able to do enclosed contents room. And this was very important for understanding the motion that the building and its contents feel. A couple of other objectives arose because of the building configuration. It was somewhat asymmetric, unequal bay widths in one direction. This gave us a chance to compare the torsional response in each configuration. We also had these added mass blocks at each floor level to simulate live load, and they were in a somewhat asymmetric configuration. And the roof level in particular, we added a significant amount of mass to represent roof equipment, but it was also in a strong asymmetric configuration. I would just be aware of that. And another not specific objective, but sort of a consequence, this building had been designed in the fixed base configuration to bolt to the shake table. As a result, down at the base level, it had these column bases with stiffeners. You can kind of see a picture here, and very shortened length of the beams between the columns, shortened span length. Also added horizontal bracing in plane. The net effect of this was to really stiffen up that base level, and I'll talk about the consequence of that for one of the isolation systems. So without going into a whole lot of detail about the design process for each isolation system, I'll just show you a comparison of their resultant hysteresis force deformation. The triple pendulum system on the left, the system with lead rubber bearings on the right. You can see the difference in the post-yield period, 5.5 seconds versus 2.78 seconds. The effective period at the expected peak displacement, which was more than a meter. Well, we were targeting about a meter of displacement in the triple pendulum system and about 0.6 meters or 60 centimeters of displacement in the lead rubber bearing system. You can also see the difference in the peak base shear demand that was expected because of the shorter isolation period. The peak base shear in the LRB system was a little bit larger. Here's a picture of the triple pendulum bearings. These were very large devices, 1.4 meters in diameter. 9 identical bearings were placed, one beneath each column. The lead rubber system. So there's always this competing objective in the design of an elastomeric isolation system between displacement capacity and stability and flexibility. So generally, in order to get the flexibility and the period lengthening that you want, you need smaller devices. To increase the displacement capacity, you need larger devices. We found that according to the light weight of the building, we were really needed to limit to 4 lead rubber bearings. So we placed the 4 lead rubber bearings at the edge locations to maximize the axial load that they carried. And then we coupled those with a cross-linear bearing, which is basically a flat slider, slides bidirectionally on this rail system. And we placed those at the corners as well as the center of the building. They stabilized the elastomeric LRBs. They provided tension resistance, or we anticipated that they would provide tension resistance for overturning demands. I'll come back to that as well. Okay, so let's start out with just some basic comparative response of the 3 systems: triple pendulum, the hybrid LRB system, and the fixed base configuration. We had, because of the competing objectives, every system sort of had its own motions, but we had a few direct comparisons as summarized in this table. The first one I'll show you, this is a motion from the Tohoku earthquake. It was applied in 2D without vertical in each configuration at the same intensity in both base isolation configurations, but it had to be scaled down in the fixed space building because they're concerned about the demands and the safety. So I'll show you a little video clip of one of the contents rooms from that, that motion, the 2 isolation on the left. All right, then you can hear it as well. The fixed base building on the right. There was no damage in this system, but you can definitely see the difference in the motion that the building feels. There's much more disruption to the contents with the fixed base configuration. How that translates quantitatively, we compare the floor accelerations. Floor accelerations being most important in terms of many of the non-structural components and contents. This is what I call an acceleration profile, peak acceleration versus recorded at each floor over the height. The first one shows the absolute values. The second one shows normalized by peak ground acceleration, which is useful since each of the systems was subjected to different demands. And you can see the difference, the two isolation configurations, triple pendulum bearing in blue, lead rubber bearing in red, both attenuate the peak ground acceleration as expected. And there's a little bit of difference between the two in terms of the longer isolation period being able to attenuate a little bit more. But both are very effective when compared to the fixed base building, where you see the peak acceleration, the ground acceleration being amplified over height by a factor of about 3, which is typical, what we expect and what we design for, considering that the system remains elastic. I'll summarize some of the other minor lessons before moving on to some other things. The isolator displacements in each system could be well predicted by typical modeling techniques. We had our pre-test predictions, and in the lead rubber hybrid system, we basically were able to nail this and predict this displacement demands very well prior to the test. We didn't do as well in the triple pendulum system, and in fact, we were expecting a peak displacement demand of around 1 meter, which I mentioned. We only got a maximum of 70 centimeters, and that sort of left us scratching our head. What happened? The graduate student that was working on that aspect of the test went back and looked at the data real carefully, calibrated the friction that was observed in these dynamic trials, and adjusted the model to account for that. And what we observed or realized that because the friction pendulum bearings in this particular test were very lightly axial loaded compared to what they would be in a typical field application, the friction was higher than anticipated. And so once we accounted for the increase in friction, we were able to predict the displacement demands very well. The second bullet, with regard to the rotational demands, the torsion in the system. Larger rotational deformations were observed in the hybrid lead rubber bearing system than in the triple pendulum bearing system by about a factor of 4. And this shows, which was always known, but really confirmed the ability of these friction bearings to mitigate torsion by, regardless of the configuration, they generate a force that's proportional to the mass carried. So that sort of naturally balances any mass eccentricities that might be observed in the model. With regard to the torsional or rotational deformations that were observed in the other system, there was a lot of discussion about whether this system was ideally configured to resist torsion. And the fact that there's only a few bearings means that, you know, we didn't have a lot of options versus in a practical design application with many bearings, you can kind of design your way out of that approach. However, I would comment that even with the bearings at the edge location rather than the corners, and the corners probably would have been better for resisting torsion, but even at the edge location, compared to typical applications, this system was torsionally rigid. There's a lot of stiffness on the outside of the building. So compared to that, compared to a real application, that would be expected to limit torsion somewhat. The third bullet, larger residual displacements were observed in the triple pendulum system than the LRB system. Difference was about an order of magnitude, and 10 centimeters might be considered significant. This was purely a consequence of the strategy to design for the longer isolation period and not the specific devices. But again, there was a lot of discussion among this, about this among practitioners and whether, you know, the 10 centimeters was acceptable and how you design for it and accommodate that. there was definitely discussion that an aftershock would recenter the system, and some evidence as we continued to run these motions in sequence that the next run basically cancels out the residual displacement in the previous run. So a small aftershock potentially could recenter the system, but I don't know that you could take that as a guarantee. All right, then move on to the next issue, which was the influence of vertical excitation. And I have to say that really vertical excitation sort of stole the show, and we probably should have been expecting this, but we weren't. So I'll start out by showing just a representative run. I pick on the hybrid LRB system, but I really needn't because the effect was basically the same in all three. But what happened to the non-structural components, the contents under vertical input, and this is a 0.5 G PGA at the table level. I'll run a little video here. This was about the level at which we started to see serious consequences of the vertical. Ceiling tiles were falling. The pipes were rotating and loosening up, and the more significant disruption of the contents. Again, I think it's pertinent here to point to a direct comparison to the three systems. And so we did have a direct comparison of the effect of vertical. A lot of people did like it because the vertical was very large in each case, more than 1 G. Again, the motion was the Northridge Rinaldi receiving station recorded motion from the Northridge earthquake is known as a very wicked near-fault motion with strong pulses in both the horizontal and vertical. Anyway, so we applied that. Again, reduced horizontal in the fixed base building, but the same vertical intensity in each building. These are some time histories of vertical acceleration in the three systems: the triple pendulum bearing on the left, the lead rubber bearing in the middle, and the fixed base on the right. The very bottom row shows what was recorded at the table, as mentioned, greater than 1 G in each system. The top shows what was recorded at near a column, or basically adjacent to the column on the 6th floor or roof level. There are some distinct differences here. In the triple pendulum bearing in particular, very large accelerations were recorded. What we know happened here is that under greater than 1 G shaking, since it's not tied down, the whole building basically bounced on the table, on the shake table, and the impact of that drove large accelerations up into the columns. The lead rubber bearing system also saw a little spike there. I think it was a similar effect with play in those hybrid cross-linear bearings. Fixed base building, you didn't see much amplification. However, I think what was really important in terms of the non-structural components and contents was the vibration out in the middle of the floor slab, and that's shown here in this second row. And again, regardless of near the column, the motion that was recorded out in the middle of the floor slabs was very similar in each case, varying from about 6.5 to 8 G. It's lower frequency than the column acceleration, and it was dominated by basically the slab vibration frequency, so determined by the stiffness of the mass of individual floor slabs. And you know, this was almost shocking. 6 to 8 G was really large vertical acceleration to be transmitted to the floors. This is a little bit, this is a video that shows what happened in each system when they were subjected to this large vertical acceleration. Each one is labeled there. And basically had the effect of taking down the ceilings, widespread damage to the tiles and the grid system and so on. There was also a lot of piping damage. And key point here, this had nothing, it was not at least for these systems, was not influenced by the isolation system. Similar damage was observed in all three systems, which is a direct effect of the vertical shaking. So the student that was working on this project decided to be as systematic as he could in understanding this effect, and went through and watched the videos for each trial and assessed the data for each trial to make some overall assessments of damage in the non-structural components, specifically the ceiling and the piping system. He divided the data into different categories: slight, moderate, and extensive damage, and then plotted those against a two-way scatter plot, if you will, peak horizontal floor acceleration and peak vertical acceleration. And what we observed from looking at that data, we really believe that, at least for the level of accelerations we saw here, the damage to ceiling and piping systems was more closely correlated to vertical acceleration than horizontal. If I draw a line here, right at about 2.5 G, the couple of exceptions, most of the time was damage-free below that vertical shaking. That's when damage start to be induced. So we can say the threshold for vertical vibration induced damage to ceiling and piping systems was about 2 to 3 G. And we also looked at the amplification from the table to the floor slabs, and as I showed before, there was significant amplification. This is the ground motion number, the trial, peak vertical acceleration recorded both at the ground and in each floor. In the next slide, or in the next plot, we normalized it by dividing by peak ground acceleration. So this is an amplification factor, if you will. You may notice it looked like peak slab acceleration increased up the height of the building. The blue one on the top is the roof level. That, we believe, was partly induced by that added mass at the roof level, caused the roof level to be the most flexible and sort of affect the levels around it as well. That may not occur in a real building, but I think the amplification factors are realistic factors of about 3 from the second floor up to about 6 on the roof. So very, very significant. So again, I come back and I ask myself, well, how does this really, these observations, how do they affect us in terms of the overall resiliency? And in terms of the damage we see, is it a big deal, or can function quickly be restored? And is there anything that we can do to mitigate it? So here's a list of damage measures that we observed. In some cases, we think they're not that big of a deal. Function can probably be pretty quickly restored. For instance, if your damage is just limited to ceiling tiles falling, you can replace those fairly easily. And may be able to resume operation of the building before they're replaced. Are there mitigation measures? Yes, in some cases, for sure, there's a lot of work being done in non-structural elements right now, and there are things that we can do to improve the response. The ones that I'm most worried about is probably equipment. I think disruption of unanchored equipment could be a big deal. It may not be easy. I mean, if equipment is damaged and is expensive equipment, it may not be that easy to fix. I think this is a lot of times what the owner is, the reason they're choosing isolation, to protect expensive equipment. So what can we do? We can anchor things as much as possible. It's not always possible to anchor equipment. The other one that I was kind of worried about is the rotation and loosening of pipes. If the joints are damaged, there's potential for leakage, widespread water damage. And so far, I don't see that there's been a lot of work to mitigate against this. I know that they exist, flexible pipe couplings for various specialty applications. I don't see them. I worry about the expense and the practicality for just standard piping operations, but it's something that could be investigated. So some of it's not that big of a deal. There are some things we can do. The other question I've been asking myself is can this vertical slab vibration be mitigated? One of the students went on to some follow-on studies to really investigate how much the slab, floor slab properties influenced the vertical vibration that was experienced. So he took a practical approach, varied slab thickness, used regular versus lightweight concrete, and these are all measures that were sort of intended to, or really would influence the stiffness and the mass and the slab vibration frequency. And he found that there really was no variation that was found to uniformly reduce the slab vibration amplification. These are some results. You see that a measure that might be effective in reducing in one case or one story would increase it in another story. So we weren't really successful in that regard. It'll take more creative measures than that to mitigate the slab vibration. All right, I'll move on to a couple of other interesting performance issues. The first one is this issue which I call the load transfer, which was specific to the hybrid LRB system of lead rubber and cross linear bearings. I'll show you some histories. These are displacement histories of the bearings, each of the 4 lead rubber bearings. You see some differences due to torsion, but they're all, you can see the long period effect in there. And what I've done in this bottom plot is to take the vector sum displacement, so that you see in each bearing the displacement peaks that were observed, okay? And below that, I'm plotting in each of the same bearings the axial force variation that was recorded from the load cell. Now we know what we expect to see in this case is an overturning effect, that as the isolator displacements move from one side to the other, the axial load will shift due to overturning. Some bearings will unload, some bearings will take on increased load. And even with the overturning effect, you can see that this plot shows predominantly that each of the bearings actually shed some loads that were kind of aligned with the displacement peaks. I say shed some load because we're taking negative to mean compressive load and positive to mean tensile load. So not only did the bearings shed load, but several of them went into tension. And if I add together the forces in all the lead rubber bearings, just lead rubber bearings, it's very evident that the lead rubber bearings are unloading at these large displacement excursions. So what's happening? The load is transferring, a net load transfer from the lead rubber bearings to the cross-linear bearings or sliders, and consistently aligned with the displacement peaks. Okay, so why is that happening? Let's look at the beginning of the test, say in the undeformed configuration, cross-linear bearings are carrying some load, lead rubber bearings are carrying some load. As both systems start to deform, shown on the bottom, the lead rubber bearings would have a tendency to shorten. The elastomeric layers rotate a little bit, the bearing wants to shorten. Left to his own devices, it would. However, the cross-linear bearing is somewhat rigid, and it doesn't shorten. And because of that base diaphragm system, there was a constraint that was sort of forcing the two bearings to remain at the same height. What that did is cause a net load to kind of pull up on the lead rubber bearing to keep it aligned with the cross-linear bearings, and that load was transferred over to the cross-linear bearings. So, summarize, this hybrid configuration of bearings was very effective to achieve some of the things we wanted: stabilize the isolation system, allow a larger displacement to be targeted and increase the isolation period, provide resistance to overturning. However, we know the rigidity of the CL bearings, and along with the base diaphragm, caused tension in some of the bearings. And so the cross-linear bearings didn't carry the tension like we were expected. Was definitely is now understood that the significant rigidity of this base diaphragm, which I mentioned at the beginning, exaggerated this effect. However, I think, you know, we had a variety of opinions like this. Some practitioners saying that, you know, the system, because of this issue, it's just not a good design option and shouldn't be used. Others saying, well, you know, you're really you're making an issue out of something that wouldn't be important in a typical application. I think my conclusion is that this is definitely something, it's not a one-size-fits-all solution. It's worth examining the effects, whether the hybrid system is a good design solution. You have to consider the flexibility of the base diaphragm and whether some of the difference between the vertical stiffness and that deformation incompatibility can be accommodated through bending of the base diaphragm, and it should probably be considered on a case-by-case basis. Okay, second major performance issue, and this was one that was really interesting to look at. To my knowledge, there hadn't ever been any other test that had showed something like this. And what we saw was basically an amplification of the horizontal acceleration due to horizontal vertical coupling. Okay, and again, I have to pick this this very large Rinaldi receiving station comparison, which we had both in 2D and 3D, to best illustrate the effect. So what I'm showing here is a horizontal floor acceleration recorded at the roof level for both the 2D, no vertical shaking in blue, and 3D with vertical shaking in red. And you can see that when vertical shaking is included, there is a big increase in the horizontal acceleration. Both the triple pendulum system, the lead rubber bearing hybrid system, but we even saw that effect to some extent in the fixed base system. As we thought about this, analyzed this, looked at the data, we boiled it down to two different coupling effects. The first one being the coupled modes of the structure itself, and the second being an issue that is specific to triple pendulum bearings due to the friction effect. So I'll discuss both of these effects. I'll start with the coupled mode effect, which really showed up in all three systems. The hybrid LRB system is the best one to illustrate this effect. I'm comparing here some acceleration histories and acceleration profiles for a 2D motion on the left and a 3D motion on the right. It's the same motion but run at a slightly lower intensity for 3D. On the left, you see basically similar to the acceleration profile that I showed you before for Iwanuma. It's basically uniform acceleration through height, reflects the uniform first mode shape that's typical with an isolated building, a little bit of a second mode. On the right, you see that perfect mode shape under the 3D acceleration is disrupted a bit, and there's a little bit more variation or scatter in the peak accelerations that are observed on each floor. Okay, so we also looked at the spectra, floor spectra recorded on every floor in the X direction and the Y direction. And this is the test data here, the 3D motion in red, the 2D motion in blue. And what I want you to observe here basically is that in the Y direction, we have additional spectral peaks for the 3D input that weren't present for the 2D input. Okay, so we did a little bit of analysis of these floor spectra. This time I'm comparing test data versus our own analysis. And you can see that with our analysis, we were able to replicate the floor spectra pretty well. This is for the 2D motion in the X direction. We see the first spectral peak shows up on every floor, we believe to be the isolation mode. The second peak, which showed up pretty strongly on every floor except the fourth floor, we believe to be a first structural mode. And it didn't show up on the fourth floor because there's a node at that location. The second peak showed up pretty strongly, or sorry, a third peak, I should say, showed up pretty strongly in the first floor, third floor, fourth, and fifth. It was absent on the second and fifth floor. We believe this represents the second structural mode, which had nodes at the second and the fifth floor. And that was basically it for a 2D motion. For a 3D motion, as I mentioned before, we saw additional peaks in the Y direction, and I kind of point those out here. They show up in every floor. We believe that they are correlated to the third structural mode, which in the Y direction, according to our computational simulations, you can see that there's some vertical slab vibration, especially at the roof level, that was included in this mode. So we believe that ultimately the vertical shaking was driving this mode and causing it to show up in a 3D motion when it didn't show up in a 2D motion, and therefore amplifying the overall acceleration. Okay, so that's the first effect, the modal coupling. Certainly buildings that have vertical irregularities, maybe setbacks and so on, would be more susceptible to this type of issue. The second effect, as I mentioned, specific to the triple pendulum bearings, I take the same approach here, and for that system, show some representative accelerations and acceleration profiles for a 2D motion and for a 3D motion. They aren't the same motion, unfortunately, but I hope this is sufficiently compelling to illustrate the effect. In the 2D motion, we see this beautiful uniform acceleration profile representing the first mode shape. In the 3D motion, especially in the X direction, we see something very different, very distinctive. And if you recall the second structural mode shape, this acceleration profile really follows that second mode shape, in that the accelerations at the second and fifth floor were much less than in the other floors. It suggests that second structural mode is being expressed somehow. The floor spectra provide further evidence. You'll see these distinct peaks at the first, third, fourth, and fifth floor, again reflecting that that second structural mode is being expressed. So the question is why? And I want to focus on the mechanics of a friction-based system and how it works. In the friction pendulum bearings, the lateral force is equal to mu, a component of it anyway, is equal to the friction component, the friction coefficient mu times the current or instantaneous axial force N. So as the building vibrates under vertical shaking, there's going to be a high frequency variation of the axial force due to vertical. And because of the friction coefficient, that high frequency axial force gets transmitted as a high frequency component that shows up in the base shear. And you can see that here in this motion. You see these little wavelets around the peak displacement peaks. These oscillations were at about 7 hertz or 0.14 seconds, which was similar to the slab vibration. Well, this particular vibration frequency happened to be coupled to or similar to that second structural mode. And so it amplified or expressed that second mode and caused it to show up in the horizontal acceleration. This was a relatively moderate, compared to some, peak vertical acceleration of 0.28 g. That Rinaldi motion that I've showed before, which had vertical accelerations greater than 1 g at the table level, caused significant axial force fluctuation from complete offloading up to about 2.5, 3 times the gravity force, and that also transmitted significant higher frequency component into the base shear. Okay, so Again, is this a big deal? Well, I want to keep in mind the big picture perspective, representative acceleration profiles for an XY motion, a 3D motion, and the fixed base building. So even though we have this amplification of the horizontal acceleration, it's still obviously much better than the baseline of a fixed base building. And we did a lot of studies that discuss the modeling, and although we weren't able to predict everything well right from the get-go, damping is a big issue and always has been in isolated buildings. But once we had a well-calibrated model, we're able to predict this pretty well, and we think we've learned some good lessons about how to do that. Big picture here in terms of the design. So seismic isolation attenuates horizontal acceleration and protects the structure from damage as expected. Increasingly, I think design of isolated buildings will be performance-driven, should be performance-driven, and performance of many components is determined by acceleration requirements. So the best way to accommodate or account for this effect is for the owner to really have strict performance requirements with regard to acceleration, to account for and evaluate the effect of the vertical shaking, and accommodate it in the design, which we can do. And I go on to say that many of the effects that were seen in the test, we believe, can be predicted by analysis and should be considered if performance requirements are strict. One of the hardest one to deal with is this vertical slab vibration, as mentioned before. So for seismic isolation to achieve resiliency, things we can do now include the effect of vertical acceleration explicitly. Code doesn't require it yet, but perhaps is moving in that direction. And then use validated best practices for non-structural component detailing. Things we might think about: a refined methodology for non-structural component design forces. ATC 120 project has been working on that. And can we mitigate the vertical slab vibration? There's clearly a lot to go in this regard, but there may be some possibilities with response control of slab vibration, floor isolation, 3D isolation. Expensive, but not out of the realm of possibilities. So I think I'm running a little over my 45 minutes, so that is pretty much concludes what I wanted to talk about, and I conclude by thanking the many sponsors for this program, including National Science Foundation, Nuclear Regulatory Commission, Earthquake Protection Systems, and Dynamic Isolation Systems and their affiliates for donating the isolation devices for this test. And then other sponsors as well, including several vendors of non-structural components. Okay, I think maybe now it's time for questions. I had quite a few references listed, and I show you the list of references here. If you are interested, you can email me for more information. And turn it over to Tommy. Thanks.
All right, thank you, Dr. Ryan. So at this point, we will look into the chat, or we will look at your raised hand. So first, there's one question right now. I will unmute you, and please introduce yourself and your question.
Hello, my name is Andres Sanchez. Thank you very much for the presentation. It's very, very good to see that there's comprehensive research on this topic. My question is, with regard to these accelerations that are in the order of 8 Gs for some of the tests, was there any damage that you can observe in the triple pendulum bearings or the rubber bearings? Is there something that you could capture and tell us about that?
Okay. So the 8G accelerations were observed in the floor slabs. As far as the accelerations that the bearings experienced, they were more limited to like 1 to 2G. And so, you know, those accelerations transmitted through the isolation systems up through the columns, which are very rigid. And then the amplification was in the floor slabs. So no damage was observed in the isolation systems. I have gotten the question before, how could the floor slab sustain the large of accelerations without being damaged? And I don't have a good answer for that. On all our studies, we've assumed they remain elastic. We didn't see any visible evidence of damage, and we haven't really had a chance to look at whether that assumption was realistic or not. It's a good question.
Okay,
Did that answer your question?
Am I still on mute?
Yeah, we can hear you.
Oh, okay. Yeah. Well, yes. One part of it, but I was thinking that. So we are looking at the shake table ground accelerations that are in the order of 1.2 Gs. So if we measure that on the top of the accelerator, wouldn't it be something in the order of 7, 8, given that the building is actually rigid?
Yeah, well, if it was completely rigid system, the amplification wouldn't be expected to be that high, would it? Anyway, it'd be, yeah. There wasn't a lot of amplification of acceleration through the isolation system. I think I should go back to maybe the slide that I lost it. Sorry. The slide that showed this, so you can have a look at it again. And literally, this is what was recorded. Yeah, so right here on the left, this is what was recorded. The table, I say, second floor, I think is actually the in purple here is actually the first floor. So yeah, I guess we saw. Oh, I'm sorry though. This is the slab. I don't have the column accelerations. No, column accelerations were pretty uniform throughout the system.
Mm-hmm.
Yeah, this in particular. This high acceleration peak that I showed in the triple pendulum bearings was a result of that impact as the isolation system touched back down on the table. So I suppose we could argue that those accelerations were transmitted through the isolators themselves. But there was no evidence of damage.
Okay, thank you. Thank you for the presentation. Very good presentation. I enjoyed it very much.
Thank you.
There's another question in the chat that is whether the result. Okay, the question is whether the results change with the properties of ground motion. Say, for example, near fault or long duration ground motions.
I assume that the comment is with regard to specifically the vertical component of shaking, and I don't know that could be clarified. But I would say that, again, slab vibration that was observed here, you do see some variations from ground motion to ground motion. Likely this is due to inherent differences in the frequency content of the ground motion, but I think the nature of some of what we saw, slab vibration, amplification, this acceleration, specifically the horizontal vertical coupling, the load transfer in the hybrid system, many of those effects were seen pretty consistently throughout the set of ground motions that we ran, which were a good mix of broadband frequency. We had one, for instance, the Mexico City earthquake that was recorded on very soft soils. We had a couple of subduction motions. And yes, some of these major trends were seen throughout the suite of ground motions, regardless of their characteristics. These are good questions, by the way.
Okay, and so if there are any more questions, we'll give it another minute or so to see in the chat, or you could unmute yourself at this point and feel free to ask. I think there was a follow-up to the previous question about are the videos available online? Are there any available videos?
There's available videos in the NERI Design Safe data archive. All of the data, pictures, videos for the project are available through NERI. I don't have anything published in a website per se. I could definitely point the interested viewer to or listener how to access some of that data through NERI, or it might be easier for me to share some of the most compelling videos through I don't want to say email, but through like a box or a Dropbox.
What I could do as well is, if you would like to share anything following up, we do post the seminar with your permission on the NERI website, and we could even add to that recommended videos to follow up with the presentation if anyone's interested to see follow-up videos. Okay, that's it. Yeah, that would be a good idea. All right, so looks like we're just about out of time. No more questions in the queue. So again, thank you, Dr. Ryan, for your presentation today. We've had a great audience and some good questions, and we look forward to your research in the future. Okay, thank you very much. It was a pleasure to share this with everyone. Okay, now to conclude today's meeting, thank you again, and please look for other NERI LEHIGH seminars coming in the future. Thank you.